then we'll do some question based on this. Let us recall what did we do in the moving charges and magnetism chapter. Let us that. Yeah. Okay. So in this chapter, what did we had? We had a current carrying wire, right? We had a current carrying wire, and so we specifically did two kinds of wire. We studied about two kinds of wire. One was this straight wire, right? And the other one was this circular wire. So for the straight wire, it had three types. One was this infinite wire. The other was a semi-infinite wire. And in the CBSE class, we didn't do this finite wire. So we will do it here. And in this circular wire, we had this full circular wire, full circle. Then we had this arc wire, right? So these were some wire that we calculated the magnetic, right? So these were some types of wire that we studied in this chapter. And apart from this, what else we studied? We and the other part that we didn't do was the toroid, right? So then also talk about this toroid. And lastly, we did this thick wire. For all these current carrying wires, we calculated the magnetic field. So for these two, right? For these two, we used circuital. For these two, we used Ampere circuital law, and for all these one, right? So this is what we studied in this. Got disconnected. Yeah, got disconnected. Magnetic field at the axial point of a wire. So this we Yeah, I got disconnected. Same thing happening. Sorry about that, Aisha. Nowadays, the internet is not working properly. Thank you for waiting, Aisha. Thank you.
It's okay.
Yeah, so now let us recap, right? And now you will help me in recapping all those portions that we have done in CBSE portion, right? So first we talked about Bio-Savart's law to calculate the magnetic field of the straight wires and the magnetic field of the circular wire. So what was this Bio-Savart's law? Let's say we have this wire and some current is flowing in this wire. So we took a small length element dl which was in this direction, right? Tangential to this one. So tangential to this. This was dl, and we were calculating the magnetic field at this point P. And let's say this was theta. So Bio-Savart's law said that the small magnetic field at this point that would be, yeah, that would be how much? Mu naught by 4 pi I dl sine theta divided by r square. So this is what the Bio-Savart's law said, right? And if we write it in the vectorial form, so this would be I dl cross r divided by r. This was the vector form, and this was the scalar magnitude form, right? Magnitude form. Okay. And to calculate the direction of the magnetic field, for direction, we used two methods. One was this thumb rule, right? And the other was this cross product, right? For straight wires, we use the thumb rule. So what was the thumb rule that what was the thumb rule that so if this is the direction in which the current is flowing, then we take our thumb with our thumb in that direction, and whatever distance we are seeing. So let's say we are calculating the magnetic field at this point. So we curl our fingers, and whatever the direction of these curled fingers shows, so that would be the direction of magnetic. So in the this is my right side, your left side. So in my right side, the magnetic field would be where? Inwards, right? And in the left side, it would be outwards. So that was the Maxwell's thumb. And we can also see the cross product. So this is dl and this is r. So we go in the dl direction, and then we go in the we curl our fingers in the r direction. So that is the direction inwards, right? So these were the two methods to calculate the direction. So in here, the magnetic field would be this cross, right, guys? And then, so this was the Bio-Savart's law, and using the Bio-Savart's law, we calculated the magnetic field, magnetic field due to a finite wire. So let's say we have this finite wire. This length and this length is fixed. For finite wire, this length and this length is fixed, right? And if we calculate the magnetic field at this point, so there would be two angles. One would be this theta 2, and this angle would be theta 1, right? So the magnetic field, let's say this current is in I current is flowing. So magnetic field due to this finite wire, this would be, let's say this distance is R. So this would be mu naught I by 4 pi R and sine theta 1 plus sine theta 2. So that is the magnetic due to this finite wire, right? And from this result, we can calculate. Yeah. So this is the magnetic field, and from this result, we can calculate the magnetic field due to infinite wire and magnetic field due to finite wire. Both the magnetic fields we can calculate. So if you guys can tell me that if we have this, let's say for infinite wire, for infinite wire, right? This is the infinite wire. This one and this length is infinite. From both the direction, this length is infinite. And then we are calculating the magnetic field at this one, right? So what would be these two angles if this wire is infinite? So let us understand that, right? What would be, if we can understand this theta 1 and theta 2, then we can easily calculate the magnetic. So let's say we have this finite wire, right? And this is theta 1 and this is theta 2, right? So if I increase this part, right, then what will happen to theta 1? What will happen to theta 1? Yes, guys, what will happen to theta 1? Will it increase or will it decrease? Yes, Aisha and Pia, what will happen to theta 1? If I increase, right? So it will, theta will increase. Okay. Now if I increase this further in here, now you see that it will again increase. If I increase this further, so it will again increase. So this theta will finally reach here. This theta will finally reach here. So then what will be theta 1 if this is infinite? What would be theta 1? Yes? What would be theta 1 if this is infinite? You see this would be the angle. So 90 degree. Is that clear? Similarly, if I increase this length, so again my theta 2 will become 90 degree for infinite wire. Okay. So if I put that value in here, so my magnetic field would be how much? My magnetic field is mu naught I by 4 pi r and sine 90 plus sine 90. So this is 1 plus 1, 2. This would be 4 pi r. And this is the result that you guys remember. Mu naught I by 2 pi r. That is the magnetic field for infinitely long wire. Right, guys? And magnetic field is cross in here because this is in. Similarly, if I calculate for semi, infinite wire. So for semi-infinite wire, this point is fixed. And then my current is infinite in one direction. So if I calculate the magnetic field at this point, so my theta 1 is 90, but theta 2 is 0. Okay. So then my magnetic field would be how much? Mu naught I by 4 pi r, and sine 90 plus sine 0. So sine 0 is 0. This is 1, so this would be mu naught I by 4 pi. So always remember these three results. For infinite wire, this is magnetic field. For semi-infinite wire, this is the magnetic field. And for a finite wire, this is the magnetic. Okay. So, and then we have the next thing that we use the Biot-Savart's law for the circular wire. Right. So for circular wire, for a full circle, the magnetic field at center was how much? Let's say we are going in this direction. So again, using the Maxwell thumb rule, and we curl our finger in the current direction. Remember, for the case of this long straight wire, we placed our thumb in current direction. But for the case of circular wire, we will place our curled finger in place of current direction. So then this would be inverse. So magnetic field due to this one is mu naught I by 2r. That is the magnetic field, right? And for semicircle, for semicircular wire, the magnetic field is how much? For this one, right? Magnetic field at this point is cross, and this is mu naught I by 4r, right? How do we calculate that? So using the Biot-Savart's law, we take this one as dl length element. This is going tangentially. This is the r distance at which we are calculating the magnetic field. So dB is mu naught by 4 pi, and I dl sine theta divided by this r square. So sine theta is perpendicular, so this is 1. dl, if we integrate, so if we integrate these two, so this would be magnetic field mu naught I is, so if we integrate dl, that would be how much, guys? That would be 2 pi r, right? So 2 pi will cancel, this will cancel, so we'll get 2r. Similarly, if we do this one, so we get 4r, right? Because this would be pi r. And for certain r, for arc wire, that would be how much? Magnetic field would be how much? This would be mu naught
Sir,
I.
can you scroll a little bit up?
Yeah, I will give the time to note it down. So I will give you guys some time to draw these.
Okay, sir.
So these parts we have done already. Just that's why I am writing them correctly, right? So for arc wire, how do we calculate? Let's say this is some arc, right? And we are calculating the magnetic field at some center. So again, we will take dl, right? And magnetic field would be mu naught by 4 pi r square I. And if we integrate this dl, right? So this would be this arc. And what is the arc length? Arc length is theta by 2 pi, right, into 2 pi r. So 2 pi will cancel, and this r will cancel, right? Okay. So this would be how much? Yeah. So this would be theta is L by r, right? So mu naught by 4 pi r, and theta. Yeah. So this one would be the result, right? For the arc length y. And again, if we use the curl of our fingers, the magnetic field would be in this direction. So these are the different magnetic fields that we calculate from different kinds of wires. For circular wires and for straight wires. And we have to always remember the directions. So you guys please note down this part, and we will do some questions based on this. So you guys please note down. And in NEET exam, we don't need to do all these things. We just have to remember all these things in our mind, right? And also there is yes, I will talk about that. Like if you, whenever you guys have noted it down, please, yes, whenever you guys have noted it down. Yes, whenever you guys have noted it down, please noted, guys.
Yes.
Yeah, then please note down. and all these results that we have to just right. This is axial point of a circular. Whenever you guys want me to scroll down, please.
Done.
Done. Okay, so please down this part. Yes, noted everyone.
Done, sir.
Uh, yeah, whenever you guys noted these steps.
Done, sir.
Down this, please note down. Whenever you guys have noted it down.
Done, sir. Done.
Done. Okay, so then
Yes, sir.
note down the circle. Yeah. Whenever you guys have noted it down,
Done.
then good. So now we have to remember more things and then we will do some questions. So then we have this Ampere circuital law. This is also used to calculate the magnetic field. So this Ampere circuital law says that if we have this current carry wire and we have this imperial loop, right? So from this area of cross section, this current is passing, and this is let's say this line is yeah. So this is the imperial loop. So closed integral of v dot ds, that would be mu naught, and this I which is so I in that is the biosense, right? Ampere circuital law, and using this one we have calculated we have calculated the solenoid. So solenoid is this one, right? And we have calculated the magnetic field. Let's say the current is flowing in this way. So we have calculated the magnetic field due to this solenoid, and this is mu naught Ni. This is very important to you. This N is what, guys? Do you guys remember what is this N? What is this N in here? Yes, guys, what is this N in here? Hmm. What is this N? Let's say in length, total length, you have N turns. Then what is this N? This is the number density, right? This is the number density, which is N by L. Right? Now do you guys remember? Yes, is that clear?
Yes, sir.
Similarly, we have a toroid. So we have a toroid in which this loop is in the form of a circle, right? So this is the kind of the loop. So if we take this solenoid and make a circle out of it, so that would be a toroid, right? I have made this horrible diagram, but you guys understand that this is a toroid, and this has an average radius. So the magnetic field due to this toroid is again mu naught Ni. Again, this is a number density. But now number density would be how much? So this would be mu naught, and this length is how much? This length is how much? So this would be n by 2 pi r. This is the length, right? This length is 2 pi r. So this would be the magnetic field due to torque. Okay, and and then we have the third thing which we will which we have understood about this Ampere circular law is about this thick wire. So we have this thick wire, right? And yeah, so we have this thick wire, and some current is flowing in this thick wire. Some current I is flowing in this thick wire. Okay. Let's say total current is flowing I. So let's say this radius is R. So what is this area of cross section? Area of cross section is how much, guys? Yes. What is the area of cross section in this thick wire? This is the area of the cross section, right? This is a say circular area. So area of cross section is pi r square, right? So in this pi r square, I current is flowing, right? So we have to remember this. This is very important to derive the magnetic field due to this thick wire. So let's say that we want to calculate the magnetic field. So there are two regions. For thick wire, there are two regions. One is inside the wire, the other is outside. So inside is this point, right? Inside is this point. Let's say this distance is small r. So let's say this distance is small r, right? So we will make a small Amperian loop, right? And in this small Amperian loop, this much current will flow. So how much current will flow in this small Amperian loop? How much would be the current? So what is this cross-sectional area? What is this area of cross-section?
Minutes.
Yeah, pi small r square, right? So in whole pi r square, the current is flowing I. So in one area, this would be pi r square. So in this region, in pi r square cross-sectional area, the current would be this one. Okay. So remembering this, let us calculate what would be the magnetic field inside. So B inside, let us figure it out. So again using the Ampere circuital law, V dot dl is mu naught I enclosed, right? I enclosed we have calculated, and V dot dl would be how much? B into small 2 pi r. Because this is the this is the Amperian loop, right? This is the Amperian loop, so its length is 2 pi r, right? So this is the length, and this is mu naught I enclosed is I r square divided by r square. So r and r cancel. So B is how much? B is mu naught I r divided by 2 pi r square. So this is B inside. So inside magnetic field is varying like what? B inside, you can see that mu naught I 2 pi r square, these are constant. So it is varying like r, right? Is that clear, guys?
Yes.
And B outside. For B outside, let's say this is the thick wire, right? And we have taken, we want to calculate the magnetic field at this point. So let's say this is some R. So we make the Amperian loop in here, right? And if we use for outside, so if we use the Ampere circuital law, mu naught I enclosed. So you guys can see that for this outer area, whole I is passive. So this would be simply I, right? And this is B into 2 pi R. So magnetic field is mu naught I by 2 pi. This is outside. So outside magnetic field is varying like how much? 1 by R. Okay. So if we plot the variation of magnetic field, so let's say this is R equal to R, and less than this R, this is inside. So inside the magnetic field is varying like this straight line, and outside it is varying like this one. So this is varying like 1 by R. So this is the magnetic field versus R for thick wire. Is this part clear, guys? Is this part clear?
Yes.
Okay, so you guys note down this part, then all the magnetic fields now we know. So then we will do some questions. So we will do some question based on. So please note it down. Yeah, whenever you guys want me to scroll down this, please. Yes. Whenever you guys have. Okay. Then, then please down that. Then, yeah, yeah. Noted, guys.
Yes.
Okay, so then this last part, please note it down. And then, whenever you guys have noted this part, please, please begin with some questions. Done? This part noted?
Yes.
Okay, so one question because the time is over. So one question we can talk about, and that one, yeah. So the variation with distance r from this question we have already done, right? So This question, a thick current wire capable of radius r. So we have this thick wire whose radius is r, and it is from this wire current I is flowing, right? So then the variation of magnetic field due to the cable with the distance r from the axis of the cable is represented by, right? So we already know that variation of B inside is R, B outside is 1 over R, right? So the variation would be from surface, right? So at the boundary, this would be this and this would be this. So this would be the variation, right? Right. This was the first question, and then all rest of the question we will do in the next. Quickly, you guys, yeah, this part you have already done, right? Okay, so we'll stop it here, and in the next class, we will